Okay, so now that we've built our model, or at least we know what one looks like, the next thing we need to do is go about estimating our parameters. We know what y is, we know what x is, so we need to try to figure out how do we go about estimating b. Because once we have b, all we'll do is figure out what's the difference between y and our main part of our model. We take the difference and we'll end up with our error term. So how do we go about figuring out what b is? So what we're going to do is we're going to try to calculate an error matrix. And this error matrix is going to be our estimate for the sigma matrix up here. And what we want to try to do is make the elements of E as small as possible. So we're going to kind of look at it in the same way we did for a univariate case, but unfortunately we're not going to end up with just a single number. So we'll take our actual amounts, kind of subtract out what our predicted amounts would be. And we want to try to make the resulting matrix the smallest it can possibly be. So in order to determine the size of a matrix, we usually take the determinant, and n times, you can't take the determinant of an n by p matrix, so instead we'll do our error matrix transpose times the error matrix again. That's kind of squaring it, and now we'll end up with a p by p matrix that we can take the determinant of. And the goal is to make that as small as we possibly can. So if we're trying to make these as small as possible, we do a little bit of vector calculus, and what we'll end up with is that our estimate for b is going to be x transpose x inverse times x transpose capital Y. And if you remember from univariate case, we end up with the exact same matrix for x. The only difference is essentially what we have is instead of dealing with y as a vector, we're going to have y as a matrix. So our estimates for each individual beta, beta 1 for y1, beta 2 for y2, beta 3 for y3, are going to be identical, as if we just did a univariate case p times. So the estimation part is essentially the same, at least for the slopes. So how do we go about fitting this model then in R? Well, what we can do is we'll use the exact same function we did for the univariate case. So what we'll do is we'll take our response variables, put it on the left side of the tilde, our explanatory variables, put them on the right, and we're just going to use the lm function again. And if we want to see the results, we do the summary command, which unfortunately, the way we've set it up in R, it's going to essentially spit out the 4 results if we did each one of these individually. So it gives us the results of LH, ML, the radius, the femur, and the tibia all kind of as their own individual sets. And the way we set it up is it doesn't look all that nice. If you notice, we have r.bones RHML. We just wanted to hopefully just say RHML. So we kind of have to do it a little of a longer way. But if we c-bind our 4 response variables and just add our explanatory variables at the end, tell it what the data set it comes from is, we make it look a little bit nicer as the results in the end. So we'll just use the exact same function we've been using in R, just now we're going to c-bind our multiple response variables together to get the results. So we have one last thing we need to estimate, is we want to try to estimate what the variance of any one observation is, given we know what their explanatory variable is. So essentially we need to try to estimate what sigma is. And this is going to look exactly the same kind of situation that we had when we were looking at MANOVA. We're going to take that estimate of E that we had of MANOVA, and we're going to use it to estimate what sigma is. So our sigma hat, or our variance of our error terms, is just going to be E divided by its degrees of freedom. And our degrees of freedom is going to be the length of Y, which is n, and we're going to subtract how many parameters we have to estimate per Y. So we end up having to subtract out q plus 1 in beta for each of our variables. So we're going to end up subtracting out the exact same thing we did for a univariate case. So we have this E matrix that we calculated, that we made as small as possible in order to estimate B. And then now we're just going to divide by its degrees of freedom n for our sample size. And then q plus 1 we subtract out for the number of parameters we estimate per set of slopes. So next thing we kind of want to figure out then was what would the variance of B B. Well, the problem is that these estimates are going to be a random matrix, and we haven't really looked at how you go about calculating the variance of a random matrix. We've always been looking at the variances of random vectors instead. So what we'll do is we'll change B from a matrix to a vector, kind of what we refer to as vectorizing it. So essentially, we're just going to take each column of B and stack them one on top of one another. So this will have q plus 1 elements, this will have q plus 1 elements, and this will have q plus 1 elements. So essentially, we're making one really long vector. And then we'll try to find the variance of this entire vector in and of itself. And again, if you take a matrix, stack the columns one on top of another, we kind of refer to it as vectorizing the matrix. So now that we vectorized B, what's the variance of that new random vector that we created? So the problem is that it's going to be huge, because if you take a vector and find its variance, if the vector has length p, then the variance matrix is going to be p by p. Well, we don't just have a vector of length p, we're going to have p q plus 1 vectors. So essentially, we're going to have p times q plus 1 is the length of this vectorized B. So that means the variance matrix is going to be p times q plus 1 by p times q plus 1. So in our example, p was 4, q was 4, so we'll end up with a 4 times 5 by 4 times 5, or a 20 by 20 matrix. So these things are going to be very, very large when we calculate them. So it's often difficult to kind of write them out in their entirety. So it's a little simpler instead to find the pair of covariances between these different slopes. So let's say I have y1 and y2. I have my two different response variables, and I want to know what's the covariances between the slopes that they have. So we'll take the slopes for yi, the slopes for yj, and then calculate their covariances, and we'll call that matrix Sij. And essentially, if you get through the math, what ends up happening is we'll have this X transpose X inverse matrix, which, if you remember, is an important part of the variance of the slopes in a univariate case. And then we multiply it in the univariate case by our estimates of the variance. And in this case, what we're going to do, we're going to multiply by the estimate of the covariance between yi and yj. So this is the covariance between the two variables whose slope we're looking at. And then what we can do is we're going to end up with a lot of these matrices that we're going to kind of stack up one on top of another. In fact, we'll end up with p times p minus 1 over 2 of these Sij matrices. The good news is they'll almost all be identical. They'll all have this same similar form, this X transpose X inverse matrix, and then we're just going to multiply all of those by a single scalar. And just the scalar is what's going to be different. So if we try to look at what it's going to be, if we look at the entire variance of our vectorized B, as you remember, each one of these is a q plus 1 by q plus 1 matrix. So this is going to be a q plus 1 by q plus 1 matrix. This will be a q plus 1 by q plus 1 matrix. So we're going to end up with a lot of these. And essentially, what this is we're taking the Kronecker product of our estimate of sigma, this SE, with this X transpose X inverse matrix. And I'll post a video of someone else explaining what a Kronecker product is a little bit better than I could.